Alright, now that we have learned much about Newton's laws, let us now deal with some more examples. Let's start off with Newton's third law. We just learned Newton's third law in the previous lecture. Now it's time to put that to work and test our understanding. We have two boxes arranged like this. One has a mass of 5 kilograms, the other has a mass of 3 kilograms, and we exert an external force of 30 newtons. That force may be exerted by a push from your hands or by a machine or whatever. That's irrelevant. But however, that external force causes this system. The system means every object that is in our current problem. We have the two boxes. This force causes this whole system to accelerate in the direction shown. Alright, what is our job? Well, our job is to find the force that exists between the 3 kilogram box and the 5 kilogram box. And how do we know that there is a force between 3 and 5 kilograms? Well, they're in physical contact, and so by Newton's third law we know that if one object is in physical contact with another object, there is a force between them. That force we call the normal contact force or the normal reaction force. Right? Let's get to it. First of all, as always, we draw our free body diagrams. Since we have two objects, we will draw two free body diagrams. We choose our axis, plus x plus y, and the first object is the 5 kilogram box. Let's call it 5. The forces are its weight, so 5 times g. It doesn't mean 5 grams. This means 5 times 9.8. That's the weight of the box. And then we have the normal force. Let's call this N5, the normal force on the 5 kilogram box, exerted by the ground on it. And then what else do we have? We have the 13 newtons force that is acting on the 5 kilogram box, the external force. So 13 newtons. All right. And is there anything else? Well, of course there is. There is the force that is due to the contact of 5 kilogram box with the 3 kilogram box, and it will always act perpendicular to the touching surfaces. Since it's a normal reaction force, then it will act on the 5 kilogram box exerted by the 3 kilogram box in the direction shown, and we don't know the magnitude of this force. Well, let's call this force F by 3 kilogram box on the 5 kilogram box, F35. Now let's draw the free body diagram for the other box, the 3 kilogram box. Let's call this box 3. What are the forces on it? We have the weight, 3 times g, and then we have the normal force. Let's call this N3. And what else? What are the other forces we have? We are ignoring friction, by the way. And so it is in contact. 3 kilogram box is in contact with the 5 kilogram box. So there will exist the same force, but in the opposite direction, right? So we have the same force, the same magnitude, the same type of force, but it will be exerted by the 5 kilogram box on the 3 kilogram box, shown as follows. So we denote this a little bit differently. We call this F5(3), meaning the force exerted by 5 on 3. Alright, and remember, this external force is only acting on the outer surface of the 5 kilogram box. It has nothing to do with 3 kilogram box. It is not being exerted on the 3 kilogram box separately. 3 kilogram box feels this force because it is in contact with the 5 kilogram box, on which this external force is directly applied to. So in this free body diagram, we won't have any 13 Newton force for the 3 kilogram box. Okay? Now what? We have drawn our free body diagrams. Our goal is to find this force, either this or that. We know that they're the same, so we can find either one. It doesn't matter which. So let's go ahead. How do we find forces? We use Newton's third law in conjunction with Newton's second law. So our next job would be to write down our Newton's second law equations for both of these boxes in the x and y directions separately. So let's write down the Newton's second law, F equals ma in the x direction. In the x direction, we have, what are the forces we have? We have F53 in the positive x direction, this force in the positive x direction, so it's a positive, and no other forces in the x direction on the 3 kilogram box. So no other force equals m times, what is the acceleration in the x direction? ma. So this whole system, both of the boxes have the same acceleration. This is, let's call it equation 1. What is Newton's second law in the y direction? For the 3 kilogram box, Fy equals may. Then what are the forces in the y direction on the 3 kilogram box? We have N3 and we have 3g. So N3 is in the positive direction, so positive N3 minus 3g is in the negative y direction, so we have negative 3g equals m times ay. What is ay? Again, the system is not moving in the y direction, so this is 0. Hence we end up with N3 minus 3g equals 0. So N3, the normal reaction force on the 3 kilogram box, is nothing but the weight of the 3 kilogram box, 3 times g, or 3 times 9.8. Let's call this our equation 2. Now let's work out the Newton's second laws for the 5 kilogram box. The 5 kilogram box will have, in the x direction, Fx equals max. The forces on it are 13 Newton in the positive x direction, so positive 13, minus F35, the contact force exerted by 3 on 5, minus F35, and there are no other forces in the x direction. Remember, we are ignoring friction, equals m times a. So what is a? It is a in the positive direction, so ma. Let's call this equation 3. Then in the y direction, let's look at the y forces. Summation of Fy equals may. Here again, this side is 0 because acceleration in the y direction is 0. So we end up with N5, the normal force exerted by the ground on 5 kilogram box is nothing but its weight, equals to 5 times g. So these are the 4 equations. What is our goal? Our goal was to find either of these forces because they are the same, so it doesn't matter which one you find. So this is our target, F35 or F53. All right. So how do we go about finding either of these forces? Well, first of all, realize that this is a Newton's third law pair, meaning their magnitude must be equal. So the magnitude of 3,5 is equal to the magnitude of 5,3. This is a consequence of Newton's third law. However, their directions are opposite to each other. So overall, we can say that the vector F35 is equal to the same size vector as F53, but in the opposite direction, denoted by this negative sign. So anywhere you see F35, you can replace it with negative F53. So F35 we see here, we replace F35 by negative F53. What does that do for us? Well, that helps us a lot because we know from equation 1 that solving for A gives me A is equal to F53 over M. Let's call this equation 5. But look at M. What is M now? Now this is for the 3 kilogram box. So M is 3 kilograms. So this M is actually 3. And what is this M? This M is actually 5. So this is M2, this is M1, doesn't matter. So this is actually a different M than this, right? So this is 5. So 5, the equation 5 in equation 3 gives me 13 minus F35, meaning minus F53, equals m times a. What is m? M is 5 here, so 5 times what is a? A is replaced by this expression, which is f53 over 3. So f53 over 3. All right, what do we have left? We have 13 minus minus gives you a plus. f53 equals 5 by 3 times f53. So let's bring all the f53s on one side. So 13 is equal to 5/3 f53 minus f53. This gives you, if you solve for f53, we have f53 equals 19.5 newtons. All right, so this is the force that 5 kilogram box exerts on 3 kilogram box. But in our question, it asks us specifically to find the force that 3 kilogram box exerts on the 5 kilogram box. That means they would be exerting the same force due to Newton's third law, however in the different directions. So that means the question actually wanted me to find F35, which should be then negative 19.5 newtons. The negative implies that this force is in the opposite direction of F53.